and above that you have a purple haze, but you don't get this liquid state in between. So under certain conditions, solids can go immediately from solid to vapor phase without going through the liquid phase, and that's called sublimation. And where these three get together, this is where all the three phases are in equilibrium with each other. That's the triple point. Okay. We have some equations describing the relations between all of these thermodynamic properties, but sometimes these are very complex, very difficult to calculate. And then it's easier to use tables, and that's where these tables come in that are at the back of the book. The thermodynamic tables with specific heats. We have specific heats, properties of common liquids and solids. We have saturated water tables. We have superheated water tables, etc., etc. So then you can just look up the numbers without having to calculate them. Okay. We are not really going into enthalpy and entropy in our course, but it is important to just give a short definition of what enthalpy is. So for lots of processes, except for that there's heat exchange, there is also work involved. You will know this from chapter 3. If you have an expanding gas, then it has to push away the atmosphere. So apart from that, you can have heat exchange between the gas in the system and the surroundings. There's also energy being exchanged because of the work that's being done. And the total energy change for a process that involves heat exchange and work, PV work, is called the enthalpy change. The change in the internal energy of a system is the change in enthalpy minus delta PV. And we can write for enthalpy, enthalpy is change in internal energy plus the PV work that's being done. Well, we'll get into that later on. Oh. And entropy, I wouldn't bother too much about it, but in general you can say that entropy is a measure of the chaos, the disorder in a system. And if we go from solid to liquid to gas, the molecular arrangement becomes more chaotic. In a solid it's neatly arranged and they cannot really move about a lot. In a liquid, they are still in contact with each other, but the molecules can move around in the liquid. And then in the gas, of course, they're bouncing all the way around in the gas in the container. So entropy increases if we go from a solid to a liquid to a gas. And we are not really doing a lot of calculations with entropy, but they are also in the tables. That's why we give a short explanation about it. Okay, one of the tables is the saturated water temperature table, and we have a saturated water pressure table. So they both give more or less the same information, but in the one table we have neat distances between temperatures, so you have 10, 20, 30, 40, 50 degrees Celsius, etc., or Kelvin. And then there's a pressure that goes with that, but those are not such nice increments. And the other table is the same table, only then the first column has 1 Pascal, 10 kilopascal, 20 kilopascal, 30 kilopascal. So it's arranged in another way, but the information that's in it is more or less the same. some of the things that you can find in there, we have a VF, that's the specific volume of the saturated liquid. And that's a bit annoying, but that's a German abbreviation of Flüssigkeit, F. And Vg, well, that's understandable. That's the specific volume of the vapor state, the gas state. In German, gas is the same. And Vfg is the difference in the specific volume of the gas phase and the liquid phase. So it's the same as V gas minus Vf. We also have enthalpies for the liquid state, for the gas state, and we have an enthalpy Fg. That's the enthalpy of vaporization. If we have an enthalpy for the gas state, sorry, for the liquid state, and we have an enthalpy for the gas state, and then the difference between these two is the enthalpy of the amount of energy it takes me to evaporate the liquid. So HFG is the enthalpy of vaporization for a specific compound. Well, and these are some examples of the tables. Let's see. Is there much more here? Oh yeah. So example question. Oh, sorry. This one. Now, during the vaporization process, a substance exists as part liquid and part vapor, so we call that quality. And quality is defined as the ratio of the mass of the vapor divided by the total mass. So if 20% of the mass is vapor and 80% of the mass is liquid, then my quality will be 0.2. It's a mass ratio between vapor and the total amount of substance that is present. So the total mass is the mass of the liquid plus the mass of the vapor, or with the German abbreviations MF plus mg. And of course quality needs to be between 0 and 1. It's a fraction.
Where do we use that for, that X?
We need it sometimes in the calculations, the quality. It comes up in some of the questions. Now, if we are dealing with a mixture, for example, in a reactor of a liquid and a gas, then to know the properties of this mixture, we would have to know, because the properties of the gas are different from the properties of the liquid, the enthalpy, internal energy, specific volume, all of that is different for liquid and for gas. Now, if you're in a reactor and you know that you have a mixture of the two, if you want to do some thermodynamic calculations, you would have to know how much is present as gas and how much of your substance is present as liquid. Otherwise, you cannot do the calculation. Now, we're going to do some kind of trick here. We say, okay, we have a saturated vapor and we have saturated liquid, and they have a mixture, and we just assume that it's a mixture which has an average specific volume or has average characteristics in general. You can also have average enthalpy and average internal energy and stuff like that. So we just assume that it's average. But then how do we know what that average is? Well, this is a long deduction. I wouldn't bother too much about it. But this one we do have to know. It says here that the quality X equals the average specific volume of my mixture minus the specific volume of the liquid part divided by the difference in specific volume of the liquid and the gas. And in some of the calculations this will come up. Okay. Now this average average value lies between Vf and Vh. So this is for a certain condition the V gas, and this is Vf, and then if we have an average, it lies somewhere in between on this line. Now, the same kind of formula you can use for other properties. You can have an average internal energy and an average enthalpy. Okay. Superheated vapor. Here, temperature and pressure are independent properties. So when you have a mixture of gas and liquid, then temperature and pressure are always dependent on each other. But if you're in the superheated region, you can change the pressure without changing the volume. Something else will have to change in your system, but here they are not dependent on each other. Let's see. Yeah. Compressed liquids, if we have a liquid that's not yet at its boiling point, that's the compressed liquid. Here the properties are relatively independent of the pressure. So if you change the pressure on the liquid, there's not a lot that changes in the liquid, in its characteristics. Temperature is more important for the thermodynamic properties of a compressed liquid. Now, if no data for compressed liquids are available, we can assume the following. At a given pressure and temperature, the specific volume, the specific internal energy, and the specific enthalpy of a compressed liquid are more or less the same as that of the saturated liquid, so the liquid that's just about to evaporate. So if you cannot find data for compressed liquids, for example, water at 80 degrees Celsius, if you cannot find data for that, just use the data for water at 100 degrees Celsius, saturated water. You can assume that it's more or less the same, its thermodynamic properties. Now, the only property that can show errors while using this approximation is the enthalpy, and to correct for this, the following equation can be used for enthalpy of a compressed liquid. The enthalpy is the enthalpy of the saturated liquid at a certain temperature plus the specific volume of the liquid times the pressure that we are working at minus the pressure at saturation point. I'm not sure whether we ever used this one in our exercises. No? Compressed liquid, reference state. This is also something we've discussed more often. In things like internal energy and entropy and enthalpy, they cannot be measured directly. So we cannot say here it's 0 and then we can measure what it is at another temperature, for example. So we cannot determine the total amount of enthalpy of a compound. We are just interested in changes in internal energy and enthalpy and entropy, not in their absolute values. Well, this means that we have to choose some kind of reference state, and where we can say, okay, here we say it's 0, it's actually not, but we have to choose some kind of point at which we say it's 0, and then we can calculate changes compared to that reference state. The reference state for water is saturated liquid at 0.01 degrees Celsius, and internal energy and entropy are assigned a value of 0 at this state. Well, compared to the reference state, sometimes properties can be positive or negative, depends on the kind of compound. The ideal, God, there's a lot of information equation just in one class. How many slides are there?
That's how I look at it too, always. I'm going through it, 10 more to go.
Oh, God. Okay. Where were we? Yeah.
65.
We all did that, no, didn't we? Let's discuss that. Yes. Well, we all know the ideal gas equation from chemistry. PV is nRT. The R that we use there is the universal gas constant, which is 8.314 joule per Kelvin per mole. But in this case, we often use this equation, which says that the pressure multiplied by the specific volume, so the volume per kilogram, equals R times T, where R is the specific gas constant, which can be found in tables. So for every compound, it has its own specific value of R. So this is the one that we most often use in this course, and not this one. We can also incorporate the molar specific volume of a substance into the equation. So specific volume is volume divided by mass, but instead of that, we can also write volume divided by the number of moles, so that's the number of cubic meters per mole, and that has the symbol V with a line above it. And in that case, we have to use the universal gas constant, but we don't use this equation often. The properties of an ideal gas at two different states are related to each other by this equation. An ideal gas doesn't really exist, but if you don't have very extreme conditions and you don't have a too high pressure, gases do act more or less like an ideal gas. So mostly gases such as air, nitrogen, oxygen, helium and argon can be treated as ideal gases with less than 1% error. Here you can see this is a TV diagram for a certain liquid. In this case it's water. The lines you see here, they connect the error, percentage of error, in assuming steam to be an ideal gas. And as you can see here, this error is 0. And here it's 0.1, 1.6, 0.5, 0.2, 0.1. So here, in this area, where this dotted line is shown, the mistake in assuming steam to be an ideal gas is very small. And you see that when we move here to the left, then it becomes much bigger. And for example, here the error is 152.7, which is very big. So if you go near the critical point, then your gas is not at all an ideal gas, and you're not allowed to use the ideal gas equation. But if you're far away from the critical point, then your gas does act more or less as an ideal gas. And where could we see that again? That was shown by this one. Do you remember the compressibility factor Z, which showed you how much your gas deviates from an ideal gas? So Z is the actual specific volume of a gas divided by the ideal specific volume of a gas. So the pressure times the actual specific volume equals ZRT. And the farther away Z is from unity, the more the gas deviates from ideal gas behavior. We can determine the value of this Z, the compressibility factor, using a reduced pressure and reduced temperature. Reduced pressure is the pressure of the gas divided by the critical pressure. Reduced temperature is the temperature of the gas divided by the critical temperature. You can also use the reduced specific volume. And then we have this graph which shows you on the x-axis the reduced pressure, on the y-axis the reduced temperature, and then here you can find the value of Z. And you see that when you have a reduced pressure, that's very small, and when you have a reduced temperature, that is almost equal to 1. No, sorry, that is... No, this is Z, yeah. This is the reduced temperature, those are the different lines. So if we have a small reduced pressure, and if we have a high reduced temperature, then we have the smallest deviation. So the more you get towards this point of your graph, the more Z equals 1, and the more your gas acts like an ideal gas. And this is another form of this graph. Again, here we have the reduced pressure. These are the reduced temperature lines. And then the ones that you see here, those are the reduced specific volume lines. So you can also use these to determine the value of Z. Okay, now that was very short a recap of number 2. Quiz number 2. Anybody any questions about it?
Thirteen.
13. Okay. It says a 1 cubic meter tank containing air at 25 degrees Celsius. And air 25 degrees Celsius and 500 kilopascal. Is connected through a valve to another tank. Containing 5 kilograms of air. At 35 degrees Celsius and 200 kilopascal. 35 degrees Celsius, 200 kilopascal. Now the valve is opened and allowed to reach thermal equilibrium with the surroundings, which are at 20 degrees Celsius. So my surroundings have a temperature of 20 degrees Celsius. So I now open the valves, and since we have pressure difference and temperature difference, probably gases will be moving around from left to right until the pressure is the same everywhere and the temperature is the same everywhere. And at the end of the process, it says there's a thermal equilibrium with the surroundings. So the final temperature in these two containers will be 20 degrees after everything has equilibrated. Determine the volume of the second tank. So we need to know what the volume is and the final equilibrium pressure of air in kilopascal. Okay, first question. How can we determine the volume in the right tank? We have a mass, we have a temperature, and we have a pressure. What relation is there between temperature, pressure, volume, etc.?
The PV is P times V is RT, which we just saw.
So we get PV is RT. That is the ideal gas law. First we have to determine, is this an ideal gas? Can I use the ideal gas law or not? Or do I have to use a compressibility factor in this case? So to determine whether or not it is an ideal gas, it says here at specified conditions air behaves as an ideal gas, but maybe it's better to just check. We have to determine the reduced pressure and the reduced temperature if we want to know that. So we have to determine the reduced pressure, which is 200 kilopascal divided by the critical pressure of air. And we have to determine the reduced temperature, which is 273 plus 35 is 308 Kelvin, divided by the critical temperature of air. Now, where can we find these data? The critical pressure and temperature of air. That's already in the first appendix, I think, table A1. Yeah, table A1, molar mass, gas constant, and critical point properties. The first substance mentioned here is air, and it says that the critical pressure is 3.77 megapascal, and the volume, the critical temperature is 132.5. So, 3.77 megapascal is 37.7 kilopascal. Is that correct? No. 1 megapascal is 1,000 kilopascal, so it's 37, was it? 3,700 kilopascal. And the critical temperature is 308 Kelvin divided by 132.5. Kelvin. If we look back at our graph here, you see that if the temperature, reduced temperature, is higher than 2, then we are almost always at a Z value of 1. And the reduced pressure here is smaller than it's 0.05 approximately, I think, the value. So we are somewhere here at this line, so it means that we are almost here somewhere in the graph if we fill in these two values. So we have a Z value that's more or less equal to 1. So this means that it is an ideal gas, or we can treat it as one. Okay, knowing that, exercise, no, not exercise class, sorry. Here we have to be, yeah, this question, question 13. So we can say that it acts as an ideal gas. Now, which of these data do we know?
Or except specific volume.
We know the pressure, which is 200 kilopascal. We know the gas constant for air, we can find it in a table. We know the temperature, which is 308 Kelvin. You have to use SI units for, of course. And the specific volume is the volume divided by the mass. So from this, we can calculate the specific volume. I don't know exactly what the value is. And this is volume divided by mass. And we know the mass, which is 5 kilograms. So we can calculate a volume from that. So using the ideal gas equation, we can calculate the specific volume. And if we have the specific volume and we have the mass, 5 kilograms, we can calculate the volume of this gas. And let's see.